test questions, not will this be on the test sorts of questions. Yes?
So if there's no fixed point, can we say it's not contraction mapping?
No.
We can't. But if it is contraction mapping, then there is a fixed point.
It's closed in the set.
It's on the
Close
set.
set, yeah.
Yes. And if you're asked to state the contraction mapping principle, makes you put in all the hypotheses. Yes.
Win-win nudge.
No, it's definitely not true that no fixed point implies nothing. Well, I mean, that is true. No fixed point implies nothing.
Well, yeah, because if a contraction mapping implies a fixed point, then no fixed point implies no
But
contraction.
Yeah, so that's
What he said.
No, but
That's what he meant to say.
Okay.
No, that's not true.
so that is what I said. That is.
That's only true on a closed.
He's saying no. That's why I'm
On a
confused.
closed.
Yeah, it has to be on a closed interval to guarantee it.
I mean, I can take this interval and stretch it and slide it over here. That has no fixed point.
But it's
still contraction mapping.
No.
No. Oh, so you want it?
No fixed point means it's not contraction mapping.
Yeah, unopposed.
No,
On the clo- on-
All right,
it's
so
just
if you're mapping a closed set to itself, that's the part I was
Okay.
quibbling about.
we want an open set.
So part of the hypothesis is contraction mapping, but it also has to map x to x, and x has to be closed. So there's a lot of things when you're doing contrapositive.
So that's not part of the definition of contraction mapping then, is x to itself.
It was part of my definition, but you might not think that that's part of the definition. You might just think if it maps so that it shrinks distance, that would be contraction.
Okay.
So you have to be careful about all the definitions. Next.
And that's why for like 11 and on the homework number 11, like number B, when we use like the implicit function proof,
Yeah.
whatever to do it, that's why we had to prove that it maps from some ball less than R to some ball less than R. So
Closed ball.
Right, so we say it maps X to X.
Yes.
And then we went and found that it had a fixed point. And blah,
Yes.
blah, blah. Okay.
Anything for you though?
Yeah, I can I ask another one.
Okay.
Why did like in some of the proofs we say that like that df of x is equal to I minus df of x, the magnitude, the norm?
Yeah.
Why? You just know that?
Because we were setting up, our proofs were based on looking for functions like this. To have a fixed point. And so this is built into the function basically, and it's the derivative of that we're controlling. So you're going to apply the mean value inequality, you need to have control of the derivative of this.
Oh, so
Everybody okay?
And that's for like a fixed y, right?
Yeah, that was for a fixed one. Cameron, any questions? No? Are we done, other than Jonathan?
I have more questions.
Well. All right.
Oh, I have one. Can the implicit function theorem map to more dimensions? Or like it maps like a function mapping Rn to Rn?
Actually, it was an open set, right?
Yeah, in Rn.
And we had n bigger than n, or
And if n is bigger than n, it can't act immediately make a square matrix.
right. The hypothesis of the implicit function theorem is that you're trying to give equations for some subset here. And if you have more equations than the dimension, then you're not going to have a very interesting subset.
You can't have full rank.
Or even if you did n to n and you had full rank, then basically you would get isolated points as your zero set.
But there would at least be
And if you
something
had more equations with the best rank condition you could have, you would still have you would have probably no points locally.
Can n not even equal that?
It can, but that's what I just said. If n equals n, then you're just going to get a finite number of points in a compact set.
Like n equals m and then the Jacobian is not singular.
Right.
Then you can
So
then there's-
by the inverse function theorem, it's locally invertible. So if you set it equal to 0, locally there's just 1 point. Or none.
What do you mean just one point?
I'm not sure where the points are coming from.
Yeah.
If your think about the inverse function theorem. if you're mapping on the same dimension, if the derivative at A is non-singular, then what do we say? We said locally the map is invertible. So if you set it equals 0, how many points are going to be set to 0?
1 is the only point that makes the matrix 0 0.
No, it's because of the, if f of A is 0, and you have a neighborhood on which the function is invertible, then that means the function is 1-to-1 on that neighborhood. So there's only one point that goes to 0. So locally that's the case. So what could happen? Well, it could look like our example function built out of e to the u cosine b, e to the u sine b that I did, where I showed you you had infinitely many preimages, but locally it was still invertible.
So I'm just looking at my map, because one point that made me.
If you have an invertible function, it only sends one point.
One to one with.
So there's only one point that can get mapped to 0 on this open set.
Okay.
All right, moving on.
Question.
Yeah.
So for the three definitions of manifold, does that mean that is for smooth function or sigma function?
Yes.
Smooth or sigma?
Yes.
There are
Both.
60?
It's true for both.
It's true.
Because if something's smooth, it's C1.
So C1 function, so.
So remember when I proved the inverse function theorem, I proved it for C1.
Yeah.
And then I commented and I talked about it, that if you had a CK function, you would get a CK inverse locally. And I said it was true for C infinity as well. So the same thing is true for all these theorems. If you're talking about C1, if you're talking about f being C1 here, then the implicit function theorem says you get a C1 function. If this is C infinity, you get a C infinity function.
So C1 is a less strong condition?
Right.
Okay.
But it's true for any K you pick.
Okay.
The definitions in manifolds are still all equivalent.
But to be a manifold, it just has to be C1?
Right. Although for purposes of chapter 8 that we're now in, we're probably going to want at least C3 or something. So I'm just going to say smooth.
And so you said to let the test, we can assume everything's smooth, right? you made that comment. Like from now on, we're just going to assume everything's smooth.
For no
Differential forms, but
We're going to start.
When I was talking about coefficients of differential forms, I said they were all smooth.
Okay.
Yeah. All right. I'm ready to go on. Okay. So I want to recap where we were yesterday. So yesterday, we defined the integral on a curve of a one-form omega. Right, so we had a parameterized curve. C is the image of that parameterization. And omega is a one-form, say, on an open set containing the curve, but I'm just going to write Rn. And so I went through the whole definition yesterday. We said the integral of omega, by definition, was got by pulling back the one form and integrating it on the interval from A to B. And what we went through the steps, and we saw that that was the same thing as actually integrating the component of an f in the direction of the unit tangent vector, where f is the vector field that you get corresponding to the one form. So the one form looked like take various functions times the various dx's. If you just forget the dx's and stack the vector, the functions f into a vector, you can think of a vector function, which is called a vector field, And this calculation is computing how much, as you move along the curve, how much of f is pointing tangent to the curve. So at each point, you have a unit tangent vector. And remember what ds stands for. This means you're integrating with respect to arc length along the curve. So if you take your f, and you dot your f with t, then what that means you're doing at this point is you're taking how much of f is in the tangent direction to the curve, and you're multiplying that amount by a little bit of distance as you move along the curve. So you can think about a little delta s. And you're adding up f dot t times these little s's. So I'm not going to write down all the stuff with the partition and upper and lower sums, but you're approximating something that is saying chop the curve up into a bunch of little pieces. On each little piece, take how much f is pointing tangent to your direction times the distance you moved. So if you remember from high school physics, if you have a force acting in a certain direction, and you move a certain distance in that direction, then the work is defined to be force times distance. So you should have even seen this in Calc 2 as one of the applications of integrals. Now, if the force is not in the same direction you're moving, so for example, the standard sort of application is to say, I'm taking a book and lifting it up. So I'm exerting a force in the same direction I'm moving the book. So the work I've done is the force I've exerted, which presumably is the weight of the book, maybe a little bit more, times the distance that I've lifted. Now, I've always found it puzzling, I don't think we've talked about this year yet, so from the definition of physics, if I just stand here and hold the book, I'm not doing any work. Tell that to my aching arm after 5 minutes.
Exerting a force or something. Well, it's just canceling out the forces.
So why does my arm hurt if I'm not doing anything?
Your muscles, as I understand it, is the muscles in your arm that are doing work.
Right. So there's work being done on a micro level, but not on a macro level. Nothing to do with economics.
What's the opportunity cost?
So you have all this stuff going on inside your body, as Daniel said, with muscles that are in fact doing work in the sense of physics, but it's just not manifested by my moving the book.
So you're not doing work on the book.
Correct. So the point now is that if it's not in the same distance, then of course, like if you're pulling a book up an inclined plane and you're yanking not parallel to the plane, you're yanking in some direction like that, then of course you get a dot product, because the component of the force in the direction of motion then becomes the dot product of the two vectors. And so that's what I'm doing here when I'm adding these up. This you can think of as force dot moving this amount in the direction of the curve, approximately, right? In the tangent direction at distance delta s, you're approximating moving this part of the curve by moving in the actual tangent direction. And in the limit, that approximation is supposed to be the exact interval. Okay, so this computation gives you the work done by f moving an imaginary test particle along the curve.
Is that f times t or f of t?
Say again?
Is that f times t or f
Dot T.
It's dot product.
And should there be a sum?
Yes.
Okay.
Yeah.
And then there's a limit involved.
Yeah. So this was an approximation. So I'm trying to motivate why this is the physical notion of work by saying, okay, the integral is approximated by such Riemann sums, if you like. Okay?
Is that G like specific, or is that just any theorem?
Well, I said I was talking about a parameterized curve, so I started off with a parameterization, but you now are leading me to where I'm headed. So I'm going to ignore Ken's question. Okay, so I want to do some examples here, and you will have WebWork following this track. Oh, when you get on WebWork and look, the homework assignment you just picked up, nobody actually looked at it. Did you notice anything?
Yeah,
Two web
due
works,
on
one-
next
Two
Wednesday.
WebWorks and
And lots of
One due on next Wednesday, after spring break, the other due on that Saturday.
for the WebWorks, what about when the written homeworks due?
Didn't see.
March 26th.
So not the ones after spring break, but the ones after.
Right, so you're not turning in written work when we come back from spring break, so that's why there's two WebWorks. However, I
Don't
would
delay
encourage you
something.
not to wait till the Tuesday before the last day to start it. So, just saying, you probably want to be working on it a little consistently, not over spring break though, but once you get back.
Are you opening this for spring break though?
It's
What
open.
works?
Yeah, it's open. The first one is, not the second one.
So the second one will open on Wednesday, which I'm not
Right.
So this homework assignment is clover.
All right. So, let's do an example here. So I'm going to take so I'm going to do this in R2. I'm going to take the one form nice simple one form like that, minus y dx plus x dy, and I'm going to give you three parameterized curves. So I'm going to take the following. I'm going to take the circle that goes, say, from t equal 0 to pi over 2. So what am I getting? I'm doing this, right?
Was that close on both sides?
So again,
Yes.
so I'm doing the quarter circle that goes from 1, 0 to 0, 1. I'm doing another parameterization. I'm going to do, let's see if I can figure this out. And then I'm going to do, I'm running out of letters, k of t, which is going to go 1 minus 2 t. So I have three parameterized curves here.
I know what the first one is.
I already drew the first one.
Well, no, I know what the integral is.
Oh, aren't you smart?
Thank you.
So Daniel knows the answer to the first one. Does everyone else? I basically did this one in class for you already. So what's the pullback of omega?
It ends up being dt.
It ends up being dt, just like the thing we did in class Monday. So I'll let you double check that. So I integrate from 0 to pi over 2, the function 1 dt, and I get pi over 2. Okay, let's do Roman numeral 2. What's the pullback by h?
always sub in for y.
What fun. So I get what? Minus the square root, 2t minus t squared times, what's the pullback of dx?
Negative.
Negative dt.
Where'd you get the negative sign on?
This is a minus
it's
1.
in there, yeah.
And I'm going to put the dt at the end, okay? So this was, pullback of dx is negative 1 dt. And then plus x, what's the pullback of y? Come on, people.
1 minus t times.
Or would it be that negative t over this, that square root?
Say who? Anybody want to give me a correct answer here? Pullback of
Oh wait.
1
dy.
minus t. 1
1 minus
No,
t.
it's
1 minus t over
y.
that.
Yeah, it's 1 minus t.
Over that.
Does everybody agree? Derivative of the square root is 1 over 2 square roots. But then the derivative of the inside is 2 minus 2t, so the 2 cancels with the 2, and I have. Okay, now what do I do?
Cry a little bit.
Try, okay. Well, shouldn't we maybe simplify a little bit or something?
Sure. Pull out
That's
the
just
root.
positive.
Pull out the root, and then it might look nicer.
Pull out which root?
The root 2t minus t squared.
In the numerator or the denominator?
Numerator.
Wait, wouldn't you want to just
Then you
use
get it
a
in
common
the denominator,
denominator
you can-
and multiply the top through because it'll cancel?
That would be what I would do. I'd put a common denominator on the bottom, and then what do I have upstairs?
2t minus t squared,
Plus t squared minus 2t plus 1.
which is just going to give you 1 on top.
Equals 1.
Oh, joy. You sure we didn't make a mistake?
Pretty positive because you would have stopped us.
That's a known.
You have way too much faith in me. So now we're supposed to integrate from 0 to 1. So this is a new curve. I'll call it C twiddle. It's the pullback of h upper star omega on the interval 0, 1. So unless we screwed up, we're supposed to do this integral, which by the way looks like an improper integral to me.
It really does.
It looks doubly improper, in fact. Does everybody see why it's doubly improper?
Well, no, it's not. It's not at 1.
Yeah.
It isn't?
No,
it's 2t.
It's
1, 2 minus 1 is just
Oh, 2 minus 1.
Yeah, not 0.
But it is improper though.
Did you try to?
It means
One
to
of the-
make it
one of the
no, it
ways-
doesn't make sense.
Alright, so it's only singly improper. Because it blows up t equals 0.
And why is it C twiddle and not just C?
Because C was for G.
Oh yeah,
Do we know what curve H is parametrizing?
no. Right.
We don't think it's the one from.
I don't know, do we?
Could be. Probably not.
Alright, so how are we going to do this integral, guys?
How do we know it even, I mean,
Let
since it
T
is
equals-
improper, how do we really,
Can we do?
It looks like one of the
I mean,
does it, do we just
like
need to
the
have faith?
inverse
Yeah,
things.
limit.
that doesn't define it for the we can only, it doesn't define it for the closed interval, does it?
Alright, so officially, to make Daniel happy, that's what we're doing. But how do we do an antiderivative of this?
You could pull out a T if you wanted to.
Doesn't it look like a little bit inverse trig functions?
Yeah, sort of.
If we divide bottom by like a number, like divide by 1 over 4.
Why don't we
Put that out.
Why
It
don't we
looks a
split
little
square?
bit like inverse sine, right?
Okay.
All right, Gabe, complete the square.
You did it. I believe you. It's good practice.
Well, do like negative and then parenthesis.
So this
Yeah.
looks like
Negative.
negative quantity t minus 1 squared.
Sorry.
Does it not?
Mm-hmm.
That would have a negative t squared plus a 2t, but then it would have a negative 1.
Which
So I need a 1.
That
So
was
we
like
can do it
1
simple.
minus t minus 1 times 1 plus t.
No, don't do that.
Cosine,
now you do-
cosine u. T
No.
minus 1 equals 1.
No.
So this is a
Arc sine.
Arc sine.
And we can do simple use substitution, which is guaranteed by whichever formula we just proved, whichever theorem. Change variables. Thank you.
The root of arc sine is 1 over square root of 1 minus x squared. Now, I would actually have preferred, I was taking dictation from Gabe, it's not going to matter, but I would rather have written it as 1 minus t. It's not going to matter, but I would rather do that because then I'm staying in the positive interval rather than doing negatives.
Wait.
You get the same answer.
Wait, does arc sine
Okay.
a minus b equal arc sine
Oh, actually, you don't get the same answer, do you? No, no, no.
No, wait.
Because there's a minus sign when you do the derivative. Aha. Okay, so let's leave it the way Gabe had it. This is just showing Reese shouldn't trust me. Okay, so what do we do? Get arc sine of
0 minus arcsine
what's the arc sine of negative 1?
negative pi halves.
So I get negative negative pi over 2. Well, that's a neat coincidence. All right, moving right along. What's k pullback of omega?
Pi over 2.
So negative
Yeah.
t times negative dt. So just
Okay, so again, I'm going to factor out the dt. So I have negative 1 plus,
let's see, plus 1 minus t.
so what just happens here?
You get 1 minus t equals d.
It's t minus t1.
Just get dt again. But now I'm not integrating from 0 to pi over 2, Mr. Smartass. So this is a new curve, C twiddle twiddle. Of my integral is,
I feel like I'm, yeah, now it's a Wonderland or something.
now we got 1.
Yeah.
You were sort of right, we got dt again, huh? Well, all right, any conjectures, theories? So I'm curious, where do these curves start and where do they end?
Yeah. Wait, so are we doing these?
No, they all
Okay.
start with t equals 0.
I'm about to all start at the same place.
Gabe, are you trying to say something?
I have a question.
Yeah, so?
And it's going to be going back a while, and probably has been before, but now these curves, these C twiddle, 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 and this regular C, are these any curves that we can imagine? Like, are
Well, I gave you 3 parameterized curves.
Okay.
Defined by GH.
now they're
These define
Okay.
parameterized curves.
and then the
And I drew the picture of C because we all recognized it.
And
But
then-
now I'm about to ask you what the others are.
and then we just when we defined the okay, that's by the change variables there we can
Well, I haven't done any.
or anyway when we do the integral that
By definition, the integral of omega on a parameterized curve is given by pullback.
okay,
That's the definition.
all right.
But we're heading towards a question here. Yes, Cam?
So in English, what are these numbers? They are the integral of omega on the curve defined
By these parametric equations. Now, what that represents is the work done by this force field
And it's a
along
force
these
field.
respective curves. Agreed? Now, I'm asking you now, so I said this was C twiddle, C double twiddle. Daniel's already a little bit ahead of us. Where does C double twiddle go? Well, where does it start at t equals 0?
Same place. 1, 0.
Where does it end at t equal 1?
0,
0,
1.
1.
Well, okay, so it's some curve that goes from there to there.
That has the same net work.
It has the same work. Well,
But why the third one is different?
And what about the third one? Where does it, so we don't know the blue one yet. What about k of t? It goes from,
Same.
but this one you do know. What's the path?
It's just a line.
It's a line segment that goes like that.
So, like, it makes sense, the shortest path has the least work.
No.
Because work doesn't depend.
We haven't dealt with least, but what we did observe is there's less work done on C double twiddle than on C.
I thought, didn't work not depend on the path taken?
Less.
Yeah.
Is this Robert Frost?
Oh, really? That was low.
I took.
I'm sorry, I didn't use the official, like, chemistry, whatever name for it, I can't remember it.
Path independent.
So in chemistry, there are things called state variables that give you path-independent results. Clearly, the work done by this force field does depend on the path, because we got different answers.
Because we're acting on a force field, we're not just, okay, yeah.
Now let's actually understand why physically that's true. What does this, so I still haven't dealt with this guy yet. We'll
At
get
every
back to
point
it.
it pushes perpendicular to its position relative to the origin.
But that's not the right thing to think about, Daniel. What we're interested in is how does f look relative to the tangent to the curve?
That's what I'm saying, it's perpendicular. Tangent. Well, for the circle.
For the circle, it's actually tangent. This vector is everywhere, this vector field is everywhere tangent to the circle. So Lama's statement is sort of right that that's about the most work it could do given the length of the vector field. If it's pointing tangent and it has length 1 at every point, then that's the maximum work you're going to get going because you're actually tangent to the curve. So every bit of pushing the force is doing is moving you in the direction of the curve.
Is there a path that's always orthogonal to the vector field?
Well, that's a good question for you to think about. So I'll think about it. But what's happening on C double twiddle here, it's the same vector field. Is it always tangent to the line segment? No, in fact, here it's not tangent.
It's only
Right.
tangent at one point, I think.
Right, at this point it's actually going to line up tangent. Otherwise, some of the force field is wasted because some of it's pushing normal to the curve and not tangent. So it's not surprising, as Lama observed, that you got less work because the force was not pushing everywhere completely in the tangent direction.
Wait, so I thought,
Mm-hmm.
wouldn't the, maybe I'm thinking about this wrong, but wouldn't the force pushing the tangent direction mean there was less work?
No, you're adding up force dot tangents along the curve.
But this is the work.
So this is 1 everywhere on the circle, so you're getting the arc length of the quarter circle. On the line segment, it's not 1 everywhere. The angle changes, so you're getting some amount between 1 and 1/2 as you go along.
Is that force then the force in the direction?
Say again?
Is that force the force in the direction of the?
It's at the point, so remember we drew pictures of vector fields back in the fall. At the point x, y, this is the force.
Okay.
It happens, as you guys even noticed in the fall when I did examples, it happens that this force is everywhere tangent to the circles.
Mm-hmm.
But if you, at this point, it's pointing 45 degrees,
This tangent, yeah.
At this point, it's pointing that way, and as you move along this line segment, the force turns.
Well, yeah, but what I'm saying, because if you're looking at I'm asking if the reason that when you have the normal vector, when any of that force is pushing in the normal direction and not the tangent direction.
The part that's normal doesn't contribute to the integral.
Okay, so
You're only seeing the tangential part, right?
Okay, yeah. So the force in the direction is what you're
So
saying.
Cameron's question was a good question, but I'm wanting him to figure out.
Yes.
Can you find a curve that goes from here to here that's everywhere orthogonal to the vector field?
Yes, you can.
Yeah,
It's
along
not-
the
It's not smooth.
What path do you have in mind?
If you go on the x-axis, then go with the y-axis.
Cool.
Mm-hmm.
Everybody see what he's saying? So Cameron is suggesting a fourth path now, which I'm not going to write down equations for, but I'll draw on the picture. He's suggesting that you could go along here, the vector field's always pointing vertically, and then you could turn the corner and go up here, the vector field's always pointing horizontally, so along this path, the network is 0.
And this is just,
I ran out of twins. So on this path, the integral of omega on this path is 0 because f dot t is everywhere 0.
will we always be able to do that?
No.
With,
You can't, it is, if, at one point, all vectors are all the force vectors are pointing in towards that point. You're always.
Or just, the force is just always pointing up and you're trying to go from here to here.
yeah, okay.
That's a great example too.
This is-
Meanwhile, back at the ranch, what is C twiddle?
It has the same as C.
Well, just let x be 1 minus t and y be that, and we'll figure out what y and x are, or how they're related.
So I can visualize this by kind of flipping it around to what x does. X is going to linear, like think of the x-axis going from 0. You can just plot as x, y, and we'll see what's going on.
So x is 1 minus t, y is square root of 2t minus t squared.
So it's like,
So how about we try to do what you guys already did with Gabe's inspiration earlier. This is the square root of 1 minus t quantity squared, which looks a lot like, no.
Circle.
This is the,
Looks like
it's the same path that we did with C. It's just parameterizing it as a graph rather than parametrically. Hint, hint, hint.
if we went the other way, it would say.
Great question. All right, so let me just summarize here, and then I'll answer your question. So what we've observed is 1 and 2 were different parameterizations of the same path. Were different parameterizations of the same path. 3 was a different path. So, why are you not surprised by the results that 1 and 2 were the same?
Didn't we
Work
say
is the
yes?
same.
Didn't we say yesterday if you use different parameterizations, you get the same?
So the whole point of this pullback stuff is that it doesn't depend on parameterization. If you reparameterize the same manifold and pull back, you're getting the same integral. So that's by construction with differential forms.
Now, we can still get work through the pi over 2 for something that wasn't that curve.
Absolutely.
So the velocity of t doesn't matter at all.
Say
It's all the shape of the curve. It's not.
Force is related to
Right.
velocity.
the rate at which, so when you say
Yeah.
t, you meant capital T, and that's the unit tangent. But if you parameterize the same path going at different rates, it doesn't matter. All you care about is what path you actually cover. Because that's what this is saying. You're just thinking about adding up parts of the force field that are moving you tangent to the curve. And that doesn't depend on
So like
parameterization.
if you took all t's like and squared everything, and this, because it's all t's are positive, it wouldn't change anything.
Well, you have to still parameterize the same curve.
Like, no, if
So-
you took every t and said, let that equal a squared, for example.
And then a goes from 0 to the square root of pi over 2. Yeah, you get the same answer. It's the same, you're reparameterizing the same curve. Let me go back for a second. Okay, let me take the part. Go ahead.
So I'm confused about C apostrophe C tilde. Why is f dot t equal 0? So they're orthogonal. So is the force always pointing up and to the side?
Yes,
Why is that?
because of the formula.
Okay.
So if you're on the x-axis, where y is 0, f is vertical.
Okay.
If you're on the y-axis,
X is 0.
it's horizontal.
Okay.
So I drew in a little bit of it, but I didn't draw enough. Right, so along the x-axis here, it's going like this. And then here it's going like this. it's everywhere perpendicular to the path. So you're going to have a homework problem. Among your written homework problems is a question I made up 40 years ago that I'm very proud of, which is I put an ant in a force field that I give you in the problem,
Oh, come on, man.
and the ant has to walk on a path starting at the origin and coming back to the origin. And the question is, what path does he do to have the force field do maximum work on him?
Is there an anteater in the middle?
There's no anteater.
Yes. You have another problem?
Okay.
So knowing that the integral over paths C and C twiddle gave high halves, that's not enough to say that C and C twiddle are the same.
No.
So,
If three of the C's we can write as the graph of something.
Mhm.
Can we do anything with that, or?
Well, I did it here. I used the graph representation. It didn't look it to you, but it did. It looked different because I was trying to make it go backwards from right to left. That's why I had to jazz it up. But this is the graph representation.
I mean, that's still
parametric.
the image of something.
No, but it's still x square root of 1 minus x squared. The only thing is x is going from 1 to 0. And so rather than try to explain what it meant for x to go backwards with an inequality, I just wrote it in terms of changing x to 1 minus t. But that is Cameron's question I was coming back to. So suppose you take the curve C, so it's given a parameterized curve. And so by the way, as with Cameron's example there, curves don't have to be smooth everywhere. They can be piecewise smooth. And then if you want to do the calculation, you just break it up into pieces. So if I actually wanted to parameterize C prime there, I would do it in two pieces. I would parameterize the first piece, and then I'd parameterize the second piece, and I'd write the integral as the sum. And you will have lots of problems, and we'll do examples of this in class as well. All right, given parameterized curve G, let's say it goes from here to here. We can consider what I'm going to call G minus. I suppose it's grading on a curve. So what am I going to do? I'm going to do exactly what I was just talking about to Ken. I want to run backwards from B to A. But I don't know how to write down T goes from B to A. That's not, I mean, you could say it in words, but here's what I'm going to do. I'm going to take G of B plus A minus T. Does that work? Let's think about it. If T starts at A, where is this? B. And as T increases to B, what does this do? So this runs, this formula runs you on the line segment from A to B as T goes from there to there, but then this formula runs you backwards from B to A.
Because speed doesn't matter.
So what if you do equivalent having C and have your arrow going the other way?
Yes. And so this is going to be what I'm going to call C minus. That's the grading on the curve part, where you go backwards on C from end point to beginning point. So C minus is doing that. And what do you think happens to the work when you pull back by G minus instead of by G?
I think there's negative.
By the chain rule, you get a minus in the dt, and everything else is the same.
It's the same.
You can look at but you can look at the picture because
It's like going up a mountain versus down a mountain.
when you dot the tangent vector, it turns
The
negative.
tangent vector's turned around. That's exactly right.
So while speed doesn't matter, direction
Direction
does.
matters.
So not all.
Which is coming back to what I was talking about yesterday when I was talking about orientation, and I said I'd explain it later.
And this is also why it's important that the speed is non-zero, because then it could turn around and have multiple.
Actually, that won't matter. If you do the work, if you parameterize your curve, and you go like this, you'll get the same work as if you just went. Because what happened is, when you went back and forth here, those canceled out.
Oh,
What if you?
So it doesn't hurt if you retrace your
So
steps.
you could go up, retrace your steps back to the origin and take a better line, and it'd be like the same.
As long as you're staying on the same path retracing your steps doesn't hurt. You can't change the path.
So if you retrace your steps back to the beginning,
Because you're like, this was too much work.
So,
Start again.
what I was just saying is the integral on C minus is the negative of the integral on C. And you can actually just write down using that parameterization I gave you. All right. So what did we decide? So we decided that for that force field, the work depended on path. But surely there are some force fields, you guys have had some physics, most of you, surely there are some force fields that have the property. Are there Fs, correspondingly omegas, for which the work so in the force notation it's the integral of f dot t ds, or in the one form notation is the integral of omega, for which the work depends only on the endpoints, on where you start and where you end. And I'm asking, are there such Fs?
The path doesn't matter, the direction of the path.
Yeah, starting and ending, right?
Well,
So,
certainly when the work is 0.
No, because you showed an example where the work was 0, but it was path dependent.
It's just like
No, if you go the other way.
certain
that's-
I'm not worrying about, I'm starting and ending. Start and end, stay start and end. You don't switch beginning and end. Such a force is called conservative. Nothing to do with Lama's political leanings here.
I hate those liberal forces.
Well, you'll have me to deal with later.
force is still the full
So-
force.
I will, on Friday, after tomorrow's fun test, I will explain where that terminology comes from, and then we're going to relate it to what's this saying about omega. So what one forms have the property that the integral depends only on the endpoints and not on the particular path we took. You should have a guess based on what we talked about the other day, but we'll do this on Friday. Okay.